Hello, welcome to SPMM Revision on Demand. In this podcast, I will discuss bivariate and multivariate statistical tests. What are bivariate tests? Unlike univariate tests, we apply bivariate tests if we are interested in two variables simultaneously and want to see how they associate with each other. For example, you may want to know whether weight is associated with total duration of sleep in infants. Or you may want to know whether revision time correlates with exam scores. To study the association between one independent variable and one dependent variable, bivariate tests are most suitable. The most commonly used bivariate test of association or relationship is correlation. The concept of correlation is related to a very effective visual tool called scatter plot that is used to examine the relationship between two variables. Let us examine the association between age and systolic blood pressure. In this plot, each subject is represented by a dot, and the two observed values in each subject, one corresponding to age and the other corresponding to blood pressure, are shown as X and Y readings. A line that best fits the scattered dots is also drawn here. Now the slope of this line gives the correlation coefficient. Correlation coefficient can be positive, negative, or absent. In fact, the values of correlation can range from -1 to +1. The scatter plots here depict some examples of positive correlation. If there is a perfect linear positive correlation, then every time as the variable on x-axis increases, then the one on y-axis increases as well. In this case, the coefficient will be close to +1. You can see that the slope of the line joining the scatter plots, the best fitting line, reduces with reducing positive correlation. These set of scatter plots shown now, they depict some examples of negative correlation. If there is a perfect linear negative correlation, then every time as the variable on x-axis increases, then the y on y-axis will decrease. In this case, the coefficient will be close to -1. A correlation value close to 0 refers to an absence of relationship between the x and y variables. As shown in this figure, in this case the best fit line will appear horizontal, flat, with almost no slope. There are two types of correlation tests. For parametric data, we use Pearson coefficient. This is denoted by the alphabet R. For non-parametric data, we employ Spearman's coefficient, shown by a Greek alphabet rho. It's important to note that just because A and B are correlated, it does not mean A causes B or B causes A. In other words, correlation is not sufficient to claim causation. Moving on to the next set of tests for association, regression. Regression is seen as a step further from correlation. Regression not only tests for association, but enables us to predict value of one variable from the other associated variable using a mathematical equation. These equations can be based on either linear function employed for continuous variables or logarithmic function. Logistic regression is used for categorical variables. Ordinal regression is an extension of logistic regression that is used for predicting ordinal variables. In summary, the term predict should make you consider the choice of regression when choosing statistical tests. In this slide, a linear regression equation is examined in detail. Regression is a mathematical function to predict the value of a dependent variable, y in this case, from the values of independent variable, x in this case. The equation generally includes an error term. This is the variation in y that is unexplained by the variations in x. This is sometimes termed as the noise. The value b is the factor by which y will change for every unit of change in x. This is called the regression coefficient. In some sense, this is similar to the correlation coefficient we saw earlier. So if you want to predict someone's weight from their height, we need to determine the value of b, the regression coefficient. At this stage, it's time to introduce the concept of multivariate statistics. In the previous example, we saw that weight is influenced by height. But is height the only factor that influences somebody's weight? Certainly not. There are other factors, such as calorie intake and hours of physical activity. So, if we construct an equation, such as the one shown here, we now have greater than two variables of interest. In this case, bivariate tests are not sufficient. We need multivariate tests. We can extend our linear regression to include multiple variables as shown here. In this case, the equation is called multiple regression equation. It's one of the most commonly used multivariate tests. It's often used to study the effect of confounders on a relationship. Another multivariate test is factorial ANOVA or n-way ANOVA. Here, we are interested in studying the effect of many independent variables on one dependent variable. It's a parametric test of independent observations. An extension of n-way ANOVA is called ANCOVA. It is particularly suited for adjusting for baseline variables or confounders that can modify the effect of the independent variable on the dependent variable. Such baseline variables are called covariates, and ANCOVA stands for analysis of covariance. Another multivariate test is multivariate ANOVA or MANOVA. Here, we are interested in studying the effect of one independent variable on multiple dependent variables. This is a parametric test as well. Another multivariate test often used for data reduction is called factor analysis. It helps to detect underlying patterns in the relationships among a number of observed variables. A well-known use of factor analysis is the examination of multiple signs and symptoms of chronic schizophrenia by Liddell. Several of these multiple variables can be clustered on the basis of the high correlation among them. This property helps to identify the underlying structure of a high-dimensional multivariate space. Liddell identified the syndromes of psychomotor poverty, disorganization, and reality distortion using this approach. Path analysis is an extension of multiple regression. It allows the study of mutual influences of multiple variables on each other. In other words, this helps to study the chains of causation for putative causal pathways. Path diagrams and path coefficients are generated using this approach. Now, let's test our understanding with a best of 5 question. You are interested in sex differences and discrimination against the mentally ill. Specifically, you want to test whether women are more accepting of the mentally ill than men. You collect data from 10 men and 10 women using a scale that measures stigma against mental illness. The data is shown here. Which of the following tests would you use to test your hypothesis? The answer is unpaired t-test. Here we are comparing one variable, the stigma score, between two groups, two independent groups. Next, you suspect a relationship between training-related stress and poor exam performance among psychiatric trainees. You measure the frequency of stressful events, the perceived importance of them, and the amount of help provided by supervisors. What statistical procedure would help you to discover if exam scores can be predicted from the different aspects of work-related stress that you have measured here? Answer is multiple regression. For predicting one variable from the other, we can use regression. As there are multiple variables involved, multiple regression would be more appropriate. Now it's time to ask yourself a few questions. Thank you for choosing SPMM course for your revision.